Growth rates, polynomial v's exponential functions. Welcome. In this subsection, we will be exploring the fundamental concept of the rate of growth in mathematical functions. When we discuss the growth rate of a function, we are essentially asking a specific question. As the input variable, x, increases, how quickly does the corresponding output value, f of x, increase? Understanding this relationship is crucial because, as we will see in the following slides, different types of functions grow at vastly different speeds. This is not merely a theoretical exercise. The ability to distinguish between these growth rates has significant practical implications in various professional fields, such as physics, economics, and biology. Understanding polynomial growth. Now that we have established what we mean by the rate of growth, let us begin by examining the first type of growth, polynomial growth. First, let's look at a polynomial function of the form f sub n of x equals x to the power of n, where n is a positive integer. This specific type of function is known as a power function. The defining characteristic of these functions is that the base is the variable x, while the exponent, n, remains a constant. It is important to note that as the value of the exponent n increases, the function grows faster. To illustrate this, let us compare a few different polynomial functions. When n equals 2, we have f sub 2 of x equals x squared, which represents quadratic growth. When n equals 3, we have f sub 3 of x equals x cubed, which is cubic growth. And when n equals 4, we have f sub 4 of x equals x to the power of 4, known as quartic growth. Now, let's look at the observations. If you were to plot these functions on a graph, you would notice that as the exponent n increases, the curve becomes steeper more quickly. Consequently, for a large value of x, x to the power of 4 will be significantly larger than x squared. We have now seen how polynomial functions behave when the exponent is a constant. However, in the next slide, we will encounter a different scenario where the variable is actually located in the exponent, leading us to the concept of exponential growth. Introducing exponential growth. Now that we have explored how polynomial functions behave, let us shift our attention to a different type of function. Imagine a scenario where the base is a fixed constant, but the variable x is located in the exponent. This is what we call an exponential function. To give you a clear example of this, consider the equation y equals 10 to the power of x. It is important to notice the fundamental difference here. In the polynomial functions we just discussed, the base was the part that increased while the power remained constant. However, in an exponential function, the base stays the same and it is the power that grows. This structural difference leads to a phenomenon known as exponential growth. Unlike the steady increase we see in polynomials, exponential growth means the value of the function increases at an accelerating rate. In the next section, we will compare these two side by side to see which one eventually dominates. The comparison, polynomial v's exponential. Now that we have defined both polynomial and exponential growth in the previous slides, let us move on to a direct comparison between the two. A fundamental principle in calculus is that an exponential function will eventually grow faster than any polynomial function, regardless of how large the power, n, is. To help you visualize this, let us compare a high-power polynomial, f of x equals x to the power of 10, with a relatively simple exponential function, g of x equals 2 to the power of x. We will look at this through a step-by-step comparison as we increase the value of x. First, let us see what happens when x equals 2. For the polynomial, we have 2 to the power of 10, which equals 1024. For the exponential, we have 2 to the power of 2, which is only 4. At this stage, the polynomial is much larger. Next, let us increase x to 10. The polynomial becomes 10 to the power of 10, which is 10 billion. The exponential becomes 2 to the power of 10, which is 1024. As you can see, the polynomial is still dominating the growth. However, let us see what happens when we increase x further to 60. The polynomial, 60 to the power of 10, is approximately 6.04 times 10 to the power of 17. But the exponential, 2 to the power of 60, is approximately 1.15 times 10 to the power of 18. At this point, the exponential function has finally overtaken the polynomial. It is important to realize that once the exponential function surpasses the polynomial function, the gap between them widens at an incredible speed. In fact, no matter how large you make the power n, even if you set n to 1 million, the exponential function, b to the power of x, provided that the base b is greater than 1, will eventually overtake it. In the next slide, we will look at a real-world example to see how this astronomical growth manifests in everyday life. Real-world example: viral content. Now that we have looked at the mathematical comparison between these two functions, let us apply this concept to a real-world scenario to better illustrate the difference. Consider the spread of a viral video on the internet. First, let us look at scenario A, which represents polynomial-like growth. In this case, suppose the number of views increases based on the square of the day. This means that on any given day, x, the total views are calculated as x squared. To see how this progresses, on day 1, we have 1 squared, which is just 1 view. By day 10, we have 10 squared, resulting in 100 views. And by day 100, we have 100 squared, which gives us 10,000 views. While this is a steady increase, it remains relatively manageable. Now, let us contrast this with scenario B, which represents exponential growth. In this scenario, suppose the number of views doubles every single day. Here, on day x, the views are calculated as 2 to the power of x. Looking at the numbers here, the difference becomes staggering. On day 1, we have 2 to the power of 1, which is 2 views. By day 10, we have 2 to the power of 10, which is 1,024 views, already 10 times more than our polynomial scenario. But look at day 100. 2 to the power of 100 is approximately 1.26 times 10 to the power of 30. This is a number so large it is difficult to even comprehend. When we analyze these two scenarios, we can see that while the polynomial growth in scenario A seems steady and predictable, the exponential growth in scenario B becomes astronomical very quickly. This perfectly demonstrates the principle we discussed in the previous slide, that exponential functions eventually dominate polynomial functions. This is precisely why, when something spreads rapidly across the globe, we describe it as going viral or experiencing exponential growth. Key takeaways. Now that we have seen the real-world impact of these functions through the viral video example, let us consolidate our understanding with these key takeaways. First, let's recap polynomial growth. In a function written as x to the power of n, the base is the variable that changes, while the exponent, n, remains a constant. As we observed in our earlier slides, increasing the value of this exponent, n, will increase the overall growth rate of the function. Next, we have exponential growth. In this case, the structure is flipped. In the expression b to the power of x, the base b is a constant value, and the variable x is located in the exponent. This shift in position is what creates the accelerating growth we discussed. Finally, let's address the concept of dominance. This is the fundamental principle of this lesson. For sufficiently large values of x, any exponential function, b to the power of x, provided that the base b is greater than 1, will always eventually exceed any polynomial function, x to the power of n. As we saw in our step-by-step comparison, while a polynomial might start with a massive lead, the exponential function will always overtake it and widen the gap indefinitely. Keep this eventual victory in mind, as it is a crucial detail we will touch upon in the next slide regarding common mistakes. Common mistakes. Now, to conclude our lesson, let us address some common mistakes that students often make when distinguishing between these two types of growth. First, there is the issue of confusing the two mathematical forms. It is very common to mix up a function like x squared, which is a polynomial, with 2 to the power of x, which is an exponential function. To avoid this, always take a moment to check exactly where the variable x is located. If x is the base, the function is polynomial. However, if x is the exponent, it is an exponential function. Secondly, some students mistakenly assume that the polynomial function always loses the race immediately. As we observed in our step-by-step comparison a few slides ago, for small values of x, a high-power polynomial, such as x to the power of 10, can actually be much larger than an exponential function like 2 to the power of x. It is important to remember that this exponential dominance only occurs as x becomes sufficiently large. The exponential function may start slow, but it will always eventually overtake the polynomial.